Go.
Hello guys, this is a tutorial video of thermodynamic and heat transfer for the chapter radiation. I'm gonna guide you guys through not exactly everything, but the most important point and the main topic in radiation. Alright, let's start. Have you ever wondered how does the heat energy from the sun transfer to the earth, and how can we feel so hot every time we walk out or stay out? Now, let's go through the objectives first. Number one, I'm gonna explain to you the radiation as a mechanism of heat transfer. Number two, I'm gonna help you to understand the effect of emissivity, absorptivity, transmissivity, and reflectivity on heat transfer by radiation. Number three, apply Stephen-Boltzmann equation for calculating radiation heat transfer. And number four, real-life examples and problems. Now, the energy or the heat transferred from the sun is actually in the form of what we call radiation. The energy emitted by matter in the form of electromagnetic waves as a result of changes in the electronic configuration of atoms or molecule. Radiation is really different from conduction and convection, as the transfer of energy by radiation does not require the presence of a medium. Energy transfer by radiation is the fastest. It's at the speed of light, and it suffers no loss of energy in a vacuum. This is the method how energy from the sun transfers to the earth. Now, here comes in one of the most important law of radiation in this chapter, which is the Stephen-Boltzmann law of radiation. Radiation is a volumetric phenomenon, and all solids, liquids, and gases emit, absorb, or transmit radiation of varying degrees. The maximum rate of radiation that can be emitted from a surface at an absolute temperature is given by the Stephen-Boltzmann law as Q emit max equals to Stephen-Boltzmann constant multiple surface area multiple the surface temperature to the power of 4. Now let's talk about black body radiation. The idealized surface that emits radiation at the maximum rate is called a black body, while the radiation emitted by a black body is called a black body radiation. The radiation emitted by all other surfaces is less than the radiation emitted by a black body at the same temperatures and is expressed as Q emit equals to emissivity of the surface multiple Stephen-Boltzmann constant multiple surface area and multiple the temperature to the power of 4. The emissivity of a material is the ratio of energy radiated by a particular material to the energy radiated by a black body at the same temperature. Thus, the property emissivity, whose value is in the range of 0 to 1, is actually a measure of how closely a surface approximates a black body. You must be wondering what's the value for the emissivity of a black body. Well, it's actually equals to 1. Now, this is quite important. You really have to know the more reflective of a material is, the lower its emissivity. This is sum of emissivity coefficient for the common materials at the temperature of 300 Kelvin. Now let's go to absorptivity. Another important radiation property of a surface is its absorptivity. The absorptivity is the fraction of a radiation energy incident on a surface so that it is absorbed by the surface. Its value is in the range of 0 to 1. For the black body absorbs the entire radiation incident on it, which is why a black body is a perfect absorber as well as a perfect emitter. Now, the value for the black body is equals to 1. Since the color black is associated with nearly complete absorption of visible light, the term of perfect black body is used when referring to an object that absorbs all the electromagnetic waves falling in. In general, both emissivity and absorptivity of a surface depend on the temperature and the wavelength of the radiation. The average absorptivity of a surface is taken to be equal to its average emissivity. The rate at which a surface absorbs radiation is determined from this equation. We shall proceed to the net radiation heat transfer. The determination of the net rate of heat transfer by radiation between two surfaces. It's a bit complicated as it depends on the properties of the surface, their orientation relative to each other, and the interaction of the medium between the surfaces with radiation. In special cases of a relatively small surface of emissivity and surface area at absolute temperature that is completely enclosed by a much larger surface at absolute temperature surrounding, separated by a gas that does not intervene with the radiation, the net of radiation heat transfer from these two surfaces is determined from this equation. Now let's go to a real life situation. Have you ever feel or wonder why is it uncomfortable wearing black shirt under a sunny day? Well, it's very simple.
So we're gonna start by drawing the schematic
If you're
diagram.
wearing a lighter color
question,
or white clothes,
white
it's
cloth.
cooler to wear
So
since they
let's
absorb
draw
and
white
re-emit relatively little of the incident radiation, while
And
for
now,
the black
50
clothes,
watt
it
light
absorbs a
bulb.
large fraction of the sun's
We mentioned
radiation
that
and then
the diameter of the light
re-emit
bulb is
in
6
all directions. About 1.5 of the emitted
temperature
radiation
of
is
this light
directed
bulb,
inward
TS,
toward the
is
body and
135
creates
degrees
the
Celsius.
sensation of
And
the heat sensation, which
the
makes
emissivity
you feel warm.
is 0.8. Now,
Okay, now here
the
comes the last
of the
part,
surrounding
which we're
temperature
gonna do some
is
exercise. Read this question.
25
Take some time.
degrees
Read it
Celsius.
and understand it.
Pause. Now, we have to also make some few assumptions, which is number one, the bulb surface is a diffuse gray. Number two, the bulb, it's approximate as a sphere diameter. And number three, surroundings are large and at a uniform temperature. Okay, now the equation that we have to use is this. Now remember, all the values are given already, so what you need to do now is just really substitute it accordingly. This is 0.8 times area, surface area of us. Now, please do take note, you have to convert millimeter to meter. Multiple with the Stephen-Boltzmann constant. And lastly, the temperature. It's better for you to change to Kelvin, because your Stephen-Boltzmann equation is in Kelvin. Oh yeah, please don't forget a bracket. It's two separate things. And using a calculation, the final answer you get will be. Okay, now in the question, it wants to know that how many electrical power is dissipated to the room by radiation. So if you take 10.2 over the initial watt times 100%, you get approximately 20%. And this is the answer.